Thank you a lot. Thank you a lot. I'm very happy to be here. And thank you a lot, Josephine, for the introduction. Yeah, as he said, I'm not Rahman. So I'm the other guy over there, Rerngvit. And this talk is about determining the health of rotating machine from their vibrations. And what you see here on this picture on the back, let me start with that, is an SKF engineer who used stethoscope to look at the vibration of the asset of the machine there to determine the health back then. If you have the question in mind, they're not using that today now. They have something better, which I will show you a bit later. So, and this work is a joint work together with the gentleman from SKF, and it's a work that we did together with Combien as a joint project. Before we go into the detail of the work, let me first explain who we are as a company. You might know already SKF is the world's largest bearing manufacturer, which employ more than 40,000 people, and they have the motto of the world of reliable rotation, if you have seen in your airport, in the airport. And Combien is actually, it's more like a startup, but it's a startup that owned by many large enterprise. We're talking SKF, Electrolux, Ericsson, and our mission is to help them transform them to a digital company in the future. If you look at all those companies that Combien is helping, and SKF is an example, is there are traditional company in the sense that it is based on physical asset. And Electrolux is also based on appliance and physical asset. And in these days, it's about being digital. So our mission is how to help them to move to become like a digital company, like Google or Facebook, that better use the data. One of the team that I'm part with is specialized in how would you optimize the business process using data science. And the case that I'm going to show you is one of the cases that we recently finished and continue of the project with SKF. And it's based on this idea. Let's first give a basic idea of how this is all about. The basic idea is that any rotating machines, you have vibrations. And these vibrations are an important indicator based on the domain knowledge that we have to study and indicate the health condition. Okay? So I give you now the basic knowledge. I want to emphasize one thing. Maybe I have seen today many research investigation, which is like advanced, very state-of-the-art, based on research paper. This is going to be a little bit different angle. We're not talking about state-of-the-art. We're not talking about, okay, this is the best paper in this area. We mainly focus on the business and the impacts. And I'm going to go to the technical detail a little bit, but the focus is how you draw from the business coming into the approach and the outcome. So it's not about that it has to be the best paper in that area. Okay? Now I give you the background. Let's first go to the motivation. Why do you care about vibrations? What you see here is the people manually collected the data. This is actual device that they use today, and go to the machine, you connect the sensor, and you collect the data about vibration signal during the machine operate. And the key motivation is that you want to prevent this catastrophe, because the machine, when they operate, they have different kind of problem. You could have wrong setup, you could have deteriorations of the machine itself. So you don't want a catastrophe to happen. You want to know that beforehand. At the same time, you also cannot take it down to maintenance so often. It's not like you're going to say, every month we're going to stop the machine and have a look at it, because it's very expensive for the technician to take it down and have a look at the machine. This vibration measurement is very nice in the sense that you do not intrude the operation of the machine. You can take measurement at the same time as the machine is operated. And that's why we care about this problem. Okay? Now I give you the motivation why we consider vibration for condition monitoring. Let's now move on to a little bit business angle of this, why it is important. So here, and now just a little bit zoom into, this is the microlog analyzer, or the device that used to take the measurements. And here are the sensor, a very small sensor. And you see the direction of vibration that are being measured there. So it could be horizontal vibration or vertical vibration. So it's just to give you an example. Now, the typical way that we do vibration measurements in the world today, 90% of it are offline vibration measurements, in the sense that you send an engineer, a few engineers in to the remote location, could be some hazard locations, to take that data, connect the sensor, take the data, and then you upload it to the network, and then you have the people analyze it. Why this is important? Why this is important of it being offline? Because the algorithm and the effort could be major difference if it's an online system. If you have a lot of data all the time, that is much different context when you consider the algorithm. Because the data here is really expensive. You have to pay people to go in a danger area to collect the data. So you do not collect that often. We're talking here about something like once per month, at best, once per month. So even a period of a year, you may have 12 data points. So you have to build a model from that condition. So this is the key challenges, and that is the business angle of it, that we don't have online system. Online system is very costly. And today, for this angle, after you collected the data, for SKF, you have about 1,000 people that manually looking at this vibration signal and make a decision whether something is going to be wrong or not, to prevent that catastrophe. And it is quite important that these people spend less time to do the analysis. You have people full-time working on it, they can get tired, but at the same time, you want it to be as accurate as possible. So the key idea of this project is it feasible at all if you use machine learning to automate this process? And this is the key idea for this project. Can you apply machine learning under this offline data context? It's not about online that you have data all the time. I want to emphasize again. So this is the background business of the context. Now we move on to a little bit more technical aspect. Here are an example of the data. The vertical axis is the acceleration that you measure from that microlog device that I showed you before. The vertical axis is the time. This means the data from a single measurement when you send an engineer. So, looking at this data, we have many data scientists here. How many of you think that this vibration is going to be faulty or going to be catastrophe soon? Can you raise your hand if you think this is a faulty vibration? Okay, a few over there. Do you think this is a normal vibration? Okay, a few there. The one who not raising the hand at all, maybe you're sleeping. Okay, so the answer is we don't know. This is the case also. The challenge is that sometimes the data are missing. Some cases of real-world data, when you have real problem, the data are not perfect. Sometimes it's collected, but it's not being labeled. Sometimes certain measurement point is supposed to be measured, it's not. Because you have human as part of the process, and it's legless. So it's quite tedious to do this, taking the measurement. So sometimes they forget. So that could happen as well. So this is the aspect that you take into account as well in order to build the model. So it's quite challenging. So here, I outline the business case and then also the technical challenges to the real world. What if we just look at now the overview of the data for this particular project? So we look at the data about 30,000 machines inside one factory. And here is about very large data set. It's about 1 terabyte of vibration measurements data. However, the amount of data you eventually have is significantly lower. You see here, you start with 30,000 machines, but at the end, only 1,500 machines that actually have more than 50 samples. That's it, like very, very few data that you have, and you have to build a model from this. At this figure, on the horizontal axis, you have a median number of measurements per point, and here are the number of machines. And you could observe that actually very, very few machines that you have data, like the one that you have more than 100 here, are very few. So would you use machine learning, or would it be feasible at all? That's the question that we try to investigate. Okay, so we do the data cleaning, data pre-processing, standard machine learning techniques, and so far, so forth. I'm not going to go to that detail. The outcome that we found, we learned, is that essentially, sometimes it does work with this method. So let's first explain to you these 3 plots here are essentially the plot of different features against each other. These are the features that have been selected based on the peak-to-peak measurement of the vibration signal that I showed to you before. And this M1 HA here are the point of the measurements. So you could measure the horizontal acceleration. You could measure the horizontal velocity of the signature that you make, and you can plot against each other. What you see is that then the blue circle here are the case that it is good, so no problem with the machine. And the red triangle means it is not good. And the red area and the blue area indicate the decision boundary that coming from the algorithms. As you see in this case, actually, the feature that are informed by the domain expert in this particular area, we use much more feature than this, but this one particular case that we can show to the public. And it shows that in this case, the feature quite indicative in order to classify different class of good and not good. However, it doesn't always work. So in this another case of a similar machine, but in totally different cases, that the feature, even though from the domain expert, it does not always solve the problem. So you have something else that's missing, that the method does not address it yet, at least for today, that we have found. Okay, so now we show you 2 different cases when sometimes it works, sometimes it does not work. But what are the conditions that we mean here? We mean here in this case that you split the data time-wise. So you train on the first 70% of the data based on the time, and you test on the data that are 30% according to the time. So you basically train on the historical data and use it on the future data. This is the condition that we mean here. And what we found in terms of the issues or the challenges that I mentioned before. Sometimes you have different measurement point, but sometimes the data are not available on that measurement point. So you don't have the same semantic of the structure that you can create a feature from. And another case is that sometimes you could have a new type of fault that haven't been identified before. So you don't have basically the data inside to learn from. And this is a case that you might need some kind of new tweak and adjust a feedback loop, as the previous speaker have mentioned before, to reiterate the model. And this is another angle that we plan to look into as well. And here, I just show you the case that in this part, the horizontal axis are the time. And similar to before, the blue are good sample, the red are not good sample. And the vertical axis indicate the vibration energy, or one of the key features. And what you see, for example, here, that in this case, maybe you can cut the line, and you can see that these parts that are higher than 5 become not good, lower than 5 become good, but you still see some exception case here. So it's not always perfect. Okay. Now, this is a kind of looking a little bit into the model. What if we ignore all this and just train the model and see the overall outcome? What are the overall outcomes that we observe? And this would be the overall outcome. When you evaluate here are on the test data that the model haven't seen before. So let me give a little bit background, maybe some of who haven't seen this precision recall curve. So the precision is mean that it's a fraction of sample that being identified as faulty and being identified correctly. Let's say that the model, if the precision is 0.8, and the model identified 10 samples as being faulty, it being actually faulty 8 of them. This is mean by precision. And recall is mean it's a fraction of faulty sample that being correctly identified. If it is, say, 0.5 here, it means that half of the sample that are faulty are correctly flagged by the model. And when you see the outcome, you consider different threshold. That's why you normally present in terms of the curve instead of a single data point. And the red here indicate a flipping of a coin. Okay, and here, this is the outcome of an investigation of a short project of 4 weeks since when we have the data. So the idea is to investigate the feasibility. And the outcome here, definitely you're not going to put this thing into production because it's something that still have a lot of false positive and false negative. However, it showed that from this data, with certain pre-processing and algorithm, you can find some signal in the data. And this is the outcome that we get back to SKF, and that we're going to continue investigating this and try to move this curve to the top right area. Okay, so I have shown you the business case until the outcome. Let's now move to a little bit on how we work as a data scientist team in Combien. I also want to introduce you to the company. Probably many of you know SKF, but maybe you haven't known so much about Combien. So we currently have an office in Gothenburg. We currently have 1 person here, and we want to expand. And our office is nearby Lilla Target, where most of the tech company are. And we are owned by several different enterprises I mentioned. And these enterprises have the unique feature that they do not compete. For example, if you have SEB, you're not going to have Swedbank with Combien. If you have Electrolux, you're not going to have Siemens. And because of this setup, when we have some result, we can share within the sphere, share the model, and share the learning within the sphere. And this is the whole idea about Combien. And as a data scientist, why I think this is interesting because as a team, you have access to the data from different verticals, as similar as an employee to those companies. And as a data scientist, for example, you can 1 month work in ball bearing technology, and the next month you work in healthcare, and then the next month you can go to telecom industry. So you're not going to be one domain at the same time. And since this company can share knowledge, you could actually aggregate and find a common problem that both of them have, because both of them has big asset. Like Electrolux also have big asset. Escape also have big asset. Then you can get the data and train the model so from different domain and have even better model when you get from one single company. And each of them also, for example, many of them have churn prediction as well in terms of domain for data science. At the end, for all of them, it would be even higher business value since you can share knowledge within the sphere. Okay? And my last slide would be the shameless advertisement. So as mentioned before, we are looking for people. If you are interested to transform those traditional industry and apply your data science domains to help the business and solving real-world problem, we don't care about publishing paper. You can do it in your free time, but we care about your impact going to real-world problem. Yep. Thank you, and I'm welcoming questions.